network programming with Gen TCP and Gen UDP. In Elixir, a TCP server can be implemented using the Gen TCP module, which provides functions for controlling TCP sockets. The code establishes a TCP server that listens on the specified port number. For each client connection, it accepts the connection, spawns a new process to handle the client, and continues listening for new connections. The handle client/1 function reads data from the client, then handle receive/2 either processes the received data and sends an acknowledgement, or handles errors. HTTP clients and servers. In Elixir, you can make HTTP requests using libraries such as HTTPoison or the built-in HTTP client named HTTPotion. Below is an example using HTTPoison to make a GET request. The code defines a module myHTTP client that uses HTTPoison. A function getExample/1 is defined that takes a URL and makes a GET request to that URL. The response from the example URL is then printed to the console using io.inspect1. To use HTTPoison, you must add it to your list of dependencies in mix.xs and run mixdeps.get. Phoenix channels. Phoenix channels enable real-time communication between clients and a Phoenix server, using Websockets as the underlying transport mechanism. Clients subscribe to topics and then can send and receive messages on those topics. Typical use cases include chat applications, live updates, and interactive games. The provided code defines a simple Phoenix channel. The join3 function allows clients to join the room lobby topic. Once a client has joined, they can send messages, which are handled by the handle_in3 function. In this case, when a client sends a message with the event new MSG, the channel broadcasts that message to all subscribers of the room lobby topic using broadcast/3. The message payload is expected to be a map with a body key. Using WebSockets. WebSockets provide a way to open a bidirectional communication channel between a client and a server. In Elixir, we can use the Phoenix framework, which has built-in support for WebSockets via channels. Below is a simple example of how to set up a Phoenix channel and handle WebSocket messages. In the example, myappweb.myChannel is a custom channel module where we define WebSocket interactions. The join3 function allows a client to join a particular topic, in this case, room lobby. The handle_in3 function processes incoming messages with the event type new MSG. When such a message is received, it broadcasts the message to all clients subscribed to the same topic using broadcast/3, and the noReply socket tuple indicates that no direct reply will be sent to the client. Building REST APIs. REST, Representational State Transfer, APIs allow different software systems to communicate using HTTP requests. In Elixir, the most common way to build a REST API is with the Phoenix framework, which provides a productive and reliable way to handle web requests. The provided code is an example of a basic Elixir Phoenix controller with two actions, index and create. The index action lists all users, while the create action handles the creation of new users. The JSON2 function is used to send JSON responses. If user creation is successful, it responds with the created user object and an HTTP status code of 201 created. If it fails, it returns the errors with a status code of 422 unprocessable entity. This is a typical pattern in RESTful APIs. Overview of Ecto. Ecto is a database wrapper and query generator for Elixir. It provides a standard way to communicate with various databases, manage changesets, and perform migrations. Ecto is split into two main components, ecto.repo, which is the API to your database, and ecto.schema, used to map data to Elixir structs. Below is a simple example showcasing how to define a schema and make a query using Ecto. This code defines a simple Ecto schema for a user in an application. The schema module, myapp.user, defines the database table name, users, and the schema fields, along with their types. The changeset function takes a user struct and a map of attributes, and produces a changeset struct that can be used for inserting or updating records safely. The second part, myapp.userRepo, shows how to use Ecto repo to fetch all user entries from the database through a function called listUsers, using the myapprepo.all function provided by Ecto. Schemas. In Ecto, a schema is a way to map your Elixir structs to database tables. It provides you with a DSL, domain-specific language, to define fields, their types, associations, and other table metadata. This enables Ecto to translate between the format used in your Elixir code and the one used in your database seamlessly. In the given code snippet, we define an Ecto schema for the user entity within a MyApp Elixir application. Use ecto.schema brings the schema DSL into the module. The schema definition starts with the schema macro, which takes the table name users as an argument. Inside the block, we define fields name and age with their corresponding types. We also specify a has-many association with posts, indicating that each user can have many posts. Finally, a changeset function is defined to cast and validate user attributes when changes are being made, such as during a record insert or update. Changesets and Validations. In Elixir's Ecto, changesets are a way to filter, cast, validate, and define constraints on changes we want to apply to our data before hitting the database. They are used for both creating new records and updating existing ones, ensuring only the intended data modifications are made. In this code snippet, we define a module myapp.user, which uses ecto.schema to define the database schema for a user. Here, a changeset function is defined, which takes a user's struct and a map of attrs, attributes, to be updated. The cast3 function filters the attrs to only include the fields allowed for changes, name, email, and validate required/2 is used to ensure that both name and email fields are not empty when creating or updating a user record. Query DSL. The Query DSL domain-specific language in Ecto allows us to write queries against the database in a way that is both expressive and safe. It is built to interact with the database without the need to write raw SQL. By using Ecto's DSL, you can compose queries and take advantage of Elixir's features such as pattern matching and piping. In the code snippet, we define a query using Ecto's DSL to fetch names of users from the user table where age is greater than 18. From is a macro that starts the query. U_in_user introduces a user schema as the source. Where specifies the condition, users over 18, and select determines the data to retrieve, user names. Creating and managing repo. In Elixir's Ecto, a repo is a module that represents the database repository. It's used for querying and interacting with your database. To create a repo, you first need to add Ecto and a database adapter as dependencies in your mix.xsys file. After that, you can generate a repo using the mix task. In the code, we define a new Elixir module called myapp.repo and make it use the ecto.repo module, signaling that this is the repository module for our application. We specify the OTP app option, which should match the name of our application, ensuring that the repo will load the database configuration specific to our app. Migrations. Migrations in Ecto are a way of altering the database schema over time in a consistent and easy-to-track manner. They are version-controlled, reversible modifications such as creating or dropping tables, adding or removing columns, and changing indexes. This Ecto migration defines a module repo.migrations.createUsers that uses ecto.migration. Inside the change function, a table called users is created with columns name, email with a uniqueness constraint, and hashed password. The timestamps function is called to add inserted at and updated at columns automatically. Running this migration will execute these changes in the database. Associations and joins. Associations in Ecto are a way to express relationships between different schema entities. Common associations include belongs to, has many, and has one. Let's consider a typical blog application where you have users and posts, where a user can have many posts and each post belongs to a user. In this code, we have two modules, myapp.user and myapp.post. The myapp.user schema has a has many association to myapp.post, indicating that a user can have many posts. Conversely, the myapp.post schema has a belongs to association to myapp.user, signifying that each post is associated with a single user. These associations allow Ecto to preload relationships and construct queries across multiple tables. Advanced querying. Ecto allows you to build complex queries with joins. For instance, if you want to get posts and their corresponding authors from a blog application, you can perform a join between posts and users tables. In this example, post is the schema module for the posts table, and author is the association between the post and the user. The query uses the assoc function to perform an inner join between posts and users. It then selects the title of the post and the name of the author. Finally, the query is passed to repo.all to execute it and retrieve the results. Overview of Phoenix. Phoenix is a modern web framework built for the Elixir programming language, leveraging the Erlang VM's power to build scalable and maintainable applications. Phoenix provides tools to craft web applications and services. It's known for performance, reliability, and real-time capabilities, making it well-suited for interactive applications like chat services or live updates. Building a Phoenix project. Before we start building with the Phoenix framework, you must have Elixir installed on your machine. Phoenix also requires Hex, the package manager for the Erlang ecosystem, and the Phoenix Mix archive. Once these are set up, you can create your first Phoenix project. The code runs the phx.new task using Mix, Elixir's build tool. It creates a new Phoenix project with the default structure in a directory called myapp. This task will set up the necessary configuration and dependencies needed to build, run, and test your new Phoenix application. Routing. In Phoenix, routing is responsible for mapping incoming HTTP requests to controller actions. The router defines a set of rules to identify which controller and action should handle each request. Here's a basic example of a route definition. In this code, we create a route within a scope that matches HTTP GET requests to the /pages ID path. The colon before ID signifies a dynamic segment where the value will be passed to the controller. This route points to the show action of the page controller. Pipe through browser specifies that the request should go through the browser pipeline, which typically includes fetching sessions, rendering views, and other browser-related tasks. Controllers. In the Phoenix framework, controllers are responsible for processing the web requests, interacting with the necessary business logic, and returning the appropriate response, often by rendering views. This code defines a page controller within a Phoenix application within the myapp.web module. By using myapp.web controller, the controller inherits functionality from the web context of the app. The index function takes the connection struct, and params, a map of request parameters, and uses the render function to display the index.html template. The core prefix in params indicates that the params are not being used inside the action. Views and templates. In the Phoenix framework, views are responsible for rendering templates with data prepared by controllers. They act as a presentation layer for data, becoming the bridge between controllers and templates. This code defines a new view module, PageView, using the myapp.web application's namespace. The use macro includes the view-specific functionality from myapp.web. Views in Phoenix typically include helper functions to assist with data formatting specific to templates. Channels for real-time communication. Channels in the Phoenix framework enable real-time communication between clients and the server over Websockets. They provide a bidirectional communication channel that can handle multiple events. A typical use case for channels would be a chat application where users can send and receive messages in real time. Here's how you might set up a basic channel for a chat feature. In this code, myapp.web.chat channel defines a new channel with two functions. The join3 function is called when a client attempts to connect to the channel, chat lobby in this case. If successful, it responds with OK, socket. The handle in3 function is triggered when a message, new MSG, is received on the channel. It extracts the message body and broadcasts it back out to the channel with broadcast/3, allowing other clients to receive the message. The response, nor reply socket, indicates that no direct reply is necessary, but the connection remains open for further communication. Contexts and schemas. In Phoenix, a context is a dedicated module that exposes and groups related functionalities. It's often described as a boundary that the application's business logic lives within. It typically involves fetching, creating, updating, and deleting data, CRUD, and is meant to interact with schemas. Contexts are used to decouple and organize the business logic in a Phoenix application. Although there's no code snippet here, understanding contexts is crucial. Think of a context as a coherent collection of functions that operates on your data, which can be a part of a feature in your application, such as accounts or blogging. By encapsulating logic in a context, you can reuse code and keep your Phoenix app maintainable. Testing Phoenix applications. Testing in Phoenix is an essential part of the development process, ensuring that your web applications work as expected. Phoenix uses XUnit, Elixir's built-in test framework. Let's look at how to write a simple test for a Phoenix controller. This code defines a test case for a Phoenix application using XUnit. It sends an HTTP GET request to the /posts route and asserts that the response is successful, status 200, and contains the text listing posts. This test checks the functionality of the index action in the posts controller. Deployment options. In the Phoenix framework, there are multiple deployment options, each with its own setup and complexity. Commonly used methods include deploying with GigElixir, Heroku, Docker, and using self-hosted servers like a virtual private server VPS. Each method requires different configuration and files. For example, here's a basic Docker file setup for a Phoenix application. The provided Docker file is a list of commands for Docker to execute when building an image for your Phoenix application. It specifies the use of the official Elixir image as a base, sets up the working directory, installs hex and rebar, copies your mix files to the container, fetches and compiles dependencies, copies the rest of your application files, compiles the project, exposes port 4000, and finally, defines the command to boot the Phoenix server. Docker is a good option for deployment because it encapsulates your environment into containers, ensuring consistency across development, testing, and production. Custom mix tasks. Creating custom mix tasks can greatly enhance a developer's productivity by automating repetitive tasks. This involves defining a module with a run1 function which takes a list of arguments. The module must also use the mix.task behavior and be compiled to be available to mix. In this code snippet, we define a custom mix task named hello. By using mix.task within the module, we tell Mix that this module is intended to be a task with certain behavior. The @shortDoc attribute provides a short description of the task, which will be shown when running mix help. The run1 function is the entry point for our task, ignoring its arguments with an underscore since this particular task does not need any. It prints out a greeting to the console when invoked with mix hello. OTP Applications. In Elixir, an OTP application is a package of code that consists of multiple modules and is managed by one or more processes. It is designed to be started and stopped as a unit, and it can be run independently or as part of a larger system. An OTP application is structured around the principles of the Open Telecom Platform, OTP, a set of libraries and design principles for building robust and scalable applications. In this code sample, we define an Elixir module myapp.application that uses the application behavior, which provides a standard way to build an OTP application. Inside this module, the start2 function is where the application's supervision tree starts. The children variable defines a list of worker modules that the application supervises, and opts sets options for the supervision strategy. In this example, we use the one-for-one strategy, where if a worker crashes, only that worker is restarted. The supervisor.startLink2 function boots the supervision tree along with the defined worker S. Distribution. Elixir's distribution features allow multiple Elixir nodes, instances of the Beam VM, to communicate with each other over a network. This fosters the creation of distributed systems in which nodes can send messages to one another and manage state and computation across multiple machines. A fundamental aspect of setting up distributed Elixir is to have each node named and a shared secret for node authentication. In this example, we define a module chat with a function sendMessage3 which sends a message from one node to another. The nodes are identified by their respective names, Alice at your host and Bob at your host. The send-to function is used to send a message to a process on a different node in the network, which here is a tuple containing the message and sender's information. We need to start two IEX sessions named Alice and Bob, each running the Elixir application. Alice can call chat_send_message function to send a message to Bob's node. Notice that both nodes would need to be running on the same network and have the same cookie set for authentication to work. Node clustering. In Elixir, node clustering refers to connecting multiple Erlang nodes, potentially distributed across several machines, into a single network. This allows the nodes to communicate with each other as if they were on a single machine. Node clustering is essential for building distributed systems and applications that require high availability, scalability, and fault tolerance. The following example demonstrates how to connect two Elixir nodes on the same network. This code sample illustrates how to cluster nodes in Elixir. Initially, a module node cluster is defined with a function connectNodes that attempts to connect to another node with the specified name using node.connect/1. We assume two Elixir nodes named N1 at 127.01 and CodesDK at 127.1 are started with the same cookie, which is essential for allowing connections between nodes. In practice, cookies are used for authentication and ensuring that only allowed nodes can connect to the cluster. With node.ping/1, we can check if the nodes can communicate, returning pong if the connection is successful. To start these nodes, the IEX command is used with the -name option to specify node names and -cookie to define the cookie value. Hot code upgrades. Hot code upgrades allow a system running Elixir or Erlang to update code without stopping the system. This is crucial for systems requiring high availability. For Elixir applications, hot upgrades can be accomplished using releases with tools such as Distillery or Elixir's built-in mix release. This code snippet illustrates the module definition for handling release upgrades in Elixir. The upgrade/0 function would contain code to execute during an upgrade, like running database migrations or any other necessary tasks. When a new version of the application is released, this module is called to transition the running system to the new version without downtime. Performance monitoring and tuning. Performance monitoring in Elixir often involves leveraging tools like the Erlang Observer, telemetry, and third-party services. This example shows how to integrate the telemetry library for monitoring by emitting events. In the provided code, we define a module myapp.telemetry that sets up telemetry to listen for specific events with telemetry.attach/4. When the event myapp request handle occurs, the function handle event/4 is called, where you can process the measurements and metadata, such as logging them or sending them to a monitoring service. To start monitoring, you would call myapp.telemetry.setup at the application start.